Hi, my name is Matthew Flesher. This is a presentation on optical character recognition for text in structured text in documents or books, as well as in natural scenes. First step in OCR is dealing with noise. In the pre-processing step, there are multiple types of noise. Noise can happen from fluctuations or sudden changes in the image signal. Sometimes shots of light can distort the numerical representation of an image. Illumination is something that can happen in dealing with the text recognition. It's definitely a problem. However, it's easily fixable. You can change the brightness or the contrast and make character segmentation or line segmentation much easier. There's also, you can have dictionaries of words that sort of help with recognition, because often there's relationships between characters, and you can look up words that way. There's also filtering. This is an example of a median filter approach, where surrounding pixels are brought to the value of the median pixel in the window. This is something to eliminate outliers or strings frequencies of distorted text or light or whatever may be the case, noise in general. These things work in structured text and documents or books, but not so well in natural scenes. There's all sorts of difficulties in dealing with natural scene images or text in those natural scenes. Deep learning is something that's used nowadays. Some of the challenges are, there's multiple orientations of the text. They can be blurry. There's, numerous different fonts, and so on. Often CNNs are used generally. And generally CNNs are good for almost any object detection, but they're good to a certain point. You can't just add more networks or layers to a CNN and continue to improve on accuracy. Eventually that accuracy diminishes. ResNets are a type of neural network that always improve accuracy. They avoid what's called the vanishing gradient problem, where the updated weights always update in the direction of the gradient, which approaches zero. And eventually while the training continues, the learning stops because weights aren't getting updated. ResNets avoid this because they have skipped connections, where one layer doesn't necessarily feed into the next layer, and it might skip deeper into the network. So it's able to avoid that. Our experiments here, we used a ResNet based off of the EAST implementation that was on GitHub. It stands for Efficient and Accurate Scene Text Detector. We added a few modifications to that, and the implementation on GitHub was with ResNet. We added, it was using a sigmoid function. We changed it to a ReLU function, and we also switched the loss function from a dice coefficient to balanced cross entropy. And really, this is an attempt to train faster. It's tough to experiment with neural networks, trial and error experiments, when it takes 15 hours to train a model. The data set used was the ICDR 2015 data set. It's a pretty common data set for this type of thing. It's in a lot of different projects. It was a baseline as part of the 2015 competition for text detection. And we sped up the learning rate to 0.01. The learning rate in the GitHub was 0.000001 or something like that, but it took way too long. And this picture is an example of showing how a poorly trained net, after only with 20 images and just an hour of training, it detects almost everything as text. Our results, our accuracy was a little lower, but we did get trained much faster. And in ResNet, if there's more time in a ResNet, we could just add more nets and hopefully improve that score. The accuracy is detected by using the intersection over union approach. Just this works with any object recognition, but in text these would be rectangles of text. Here's a few more results. The graph shows baseline versus the ReLU and the BCE. The baseline is the blue, definitely performs the best. Just adding the ReLU sped up training a bit, but obviously at the cost of had more loss. However, the green green line, is adding the ReLU, but also adding just 2 more layers, where it slowed the training down a lot, but much more accurate than just the ReLU alone. And then if we actually did pretty well with the ReLU plus the balance cross entropy, that was definitely the faster one with pretty good accuracy. In the future, with more time, I'd like to add a 1x1 convolution layer in the front of the network, and that is used many times to decrease dimensionality even further by just reducing the number of channels throughout the ResNets. And so they're sort of brief down. Next, I'm going to go through collab examples, but here's where you can find the source code and the collabs here that we used. And so this is an example. First, we have to import the code. Some of this is already done because I've done this before, and this is like my 5th recording, but first we just go to get the code. Then we're going to, off of Google Drive, grab our model, which is already over here. This is what the models look like. Basically, the main part of this is the checkpoint. This one here. And so that's getting our model. It takes a bit. So then after that, we made some changes to the evaluation file. It did not quite work out of the box, but it wasn't that big of a change, but it did take a little bit. And we have to replace everything. So we can just do that. And here we're going to replace it with our code for the evaluation. We're going to get our images. They're loaded on our Google Drive from the ICDR data, and display it. And actually, it's already displayed. But this is just the bare image. There's nothing done to it quite yet. Now we're going to run the evaluation on it. This is the part that generally takes a long time. I've already ran it once, so it actually probably won't take that long at this point. But here we have, this is our text evaluator. Our code is on GitHub. And so we basically had to add, basically changing the loss function was here done in the model, and just added this function here, balance cross entropy. And this function, dice coefficient, is still there, but we're not using it in the loss function. We are switched it here and just commented that out. That's that. And this is an example of our ground truth. Let's say this ground truth for image 2. And these are XY coordinates, X1, Y1, X2, Y2. And this is the word itself. The word joint here. These are numbers. These are actual numbers that you'll find in the image. These are pound signs. They're just when we don't really care what the text is. It may be too small or something like that, but it's ground truth. It's still detected as. This is just the text detection portion, so it's not recognition. So that for this part, it doesn't really care what the actual word is. So that was in test images. We have the word joint. And here, we see that there's the word joint in there. So we're still here. We actually already pre-loaded a different image into, it was actually image 201. I just added the 2 here, but it's image 201, which we'll show later. And this is our accuracy calculator here. We can run the test on that. So this is the bad model, but it's got 441,000. At 41,000 text boxes. So it takes a little while. Well, anyway, this is eventually what it's going to look like. And for our accurate model, this isn't the bad model, but for our accurate model, which we've already run, we're going to run it again in a second, but we have calculate false positives, true positives, false negatives, and the accuracy. So we had 14 true positives out of 21. And so the false negatives are basically weren't detected, basically. So that's our evaluation. And this is the ResNet itself. So we're using this method, but they're calling this ResNet V150. So these pretty much these 2353 represent basically the blocks. This is 2 layers in one block, 3 in another block, 5 in another block, 3 in another. There's 4 blocks. So if you wanted to expand on the number of layers, you might have this one here, 2, 3, 22, 3, or down here, 2, 7, 35, 3. And from what I've seen, you definitely get more accuracy, but it takes a very long time to train. I imagine that some of these would take days, which is almost impossible. Well, it's impossible, it seems, using Colab, because Colab will disconnect from the runtime prior to. I don't think I've been able to run it for a full day thus far. So after this, we would get our pre-trained model, a better one, and basically repeat the process, which we've already done. Yeah, so I guess I'll just show it. So we get another better model here. re-download the images, retrain here. This is one that's found 212 text boxes. Maybe a different one. Or not. So anyway, we saw that the were false negatives. Basically, we had saw 14 positives. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there's 14 positives. Here's some that appear weren't detected here. Maybe this over here. Maybe the license plate that basically might have been on ground truth but not detected, basically. So they're coming out to be a false negative. And that did finally finish. So we'll run it, and it should work out to be the same image. And then we just repeat the process, which this one doesn't take nearly as long. And that was quick.